So on this video, I'll walk you through the post-lab analysis for Lab 3 atomic emission spectra. Not talking about the procedure, just the post-lab. So on the first question, you have a data table. This data table is going to contain some information that you collected during the experiment and then some information that you're calculating on your own. During the experiment, you'll be reporting the wavelength and the frequency of these 4 different lines in the hydrogen emission spectrum. One thing you need to watch out for is the units. So in this data table, you need your wavelength to be reported in units of nanometer. You need your frequency to be reported in units of hertz, which is the same thing as seconds to the -1. These may not be the units that are used in the lab. So maybe your wavelength in the lab is going to be reported in meters, and you'll need to do that unit conversion to get it into units of nanometers. Once you get your data reported here, then you'll be calculating the energy for each one of these lines. There's 2 different ways that you can calculate energy, and it's totally up to you. Energy you can calculate by using h nu. That's going to be the Planck's constant, 6.626 times 10 to the -34 times the frequency in hertz. So that would be one option that you had. The other option that you have is hc over lambda. Hc over lambda, Planck's constant, 6.626 times 10 to the -34, the speed of light in meters per second, and then the wavelength, this would need to be in units of meters. So if you wanted to use this equation, you'd have to convert your wavelength into units of meters, another unit conversion. But again, you can use either one of those equations to calculate the energy. I would probably choose this one myself just because it's a little bit mathematically easier and because there isn't an extra unit conversion. Now, if you're sharing your work or like working alongside another student, your data might fluctuate a little bit in this column. First of all, whether you're calculating your energy from the frequency or the wavelength, that could cause it to vary just a little bit. So like maybe you and your lab friend are calculating it from frequency and the other one is calculating it from wavelength. Your data might be a little different. Also, when you're reporting these wavelength values and the frequency values, even though you're all looking at the same data, you might, kind of hover the little cursor thing in a different position. So maybe you write down a wavelength of 10, but somebody else writes down a wavelength of 11. That's basically the same thing, but that is going to cause slight variations in the energy over here. So if you're comparing your work to somebody else, it might not be exactly the same, but it should be pretty close to similar. So the next 2 problems on here are going to have you using the Rydberg equations to do some calculations on the red line and the teal line that you observed. The Rydberg equation, you have that in your notes, but just kind of as a reminder, this is saying that the change in energy is negative 2.18 times 10 to the -18 joules times 1 over n initial or n final squared minus 1 over n initial squared. That's the Rydberg equation. And the goal in this problem is for you to calculate the excited energy level. The excited energy level is going to be this right here, the final. So what it's saying is that you're starting, dropping down, nope, I got that backwards. Your excited energy level is your initial, N initial. So it's telling you here that it's starting at some high energy state, which we don't know what it is, and it's dropping down to N equals 2. So N equals 2 is our final energy state. So for this, we know that this value right here is going to be 2. It's actually going to be 2 squared, and final equals 2. And then we also are going to plug in the energy. You're going to be plugging in the energy that you calculated for that particular electron. So whatever number you got up here for the red electron, for the red line, that's what you're going to plug in to this spot. And then you're just going to do the math and solve for an initial. And you'll just, want to be really careful with the squaring and all that kind of stuff. And then you'll do the exact same thing with the teal line. So this time you'll be using the energy of the teal line. Teal line is also N final is 2. They both go down to the N equals 2 level. they're not going to be the exact same number because they will have different energy. So, excuse me, circled the wrong thing. The energy value for the red line is not going to be the same as the energy value for the teal line. The data here should work out to be pretty decent whole numbers. Like when you get all said and done, you should be getting something that's in the ballpark. Like maybe you're getting an N initial is like maybe it's 2.9, which is pretty close to 3, or maybe your N initial is like 3.1, which is pretty close to 3. You shouldn't be getting anything that's like really outside the, a normal number. If you get an N initial that's like 0.5, something's gone really wrong. Check your math, do it again. And then you'll just be answering some questions about the lines. So first thing it's asking about is the red line being higher or lower in energy than the teal line. To answer that question, you've got your energy values right here. You can compare which one has higher energy. Pay attention to the exponents because that's a big deal. And then you're going to translate that into like what it means for the electron transition that resulted in the red line and the teal line. This is something that we've talked about in our notes. You'll have that in your notes about how far apart were the electron levels that resulted in those different colors. And then last but not least, identify your 4 unknowns. So to help you identify your 4 unknowns, you've got the pictures right here. You have collected your own data for your 4 unknowns, and then all you have to do is identify them. Your choices for unknowns are right here. So the 4 unknowns are all on this list, and all you have to do is just match them up.